All right, so we're going to use all of the cool stuff we've learned about inverses under multiplication and addition to start to solve equations to find the values of x that make something true. So, for example, it's easy to tell if I have 2x plus, oh, let's say 2x equals 12. Well, what would I have to multiply to x? What would I have to multiply by 2 to get 12? X equals 6. Easy peasy. But what if the problem looks like this? Holy cow, what would I have to choose? What would x have to be to make all of this equal 12? Or is there even an x that would make all of that equal 12? So we're going to start building the skills that take us to being able to solve problems like this super duper easy. So let's erase it for now because we're not quite there. And let's use properties that we have already to do some simple forms of the same thing. So let's look at the addition property of equality. Okay, it takes a long time to write, doesn't it? The addition property of equality. And what it says is, if x minus a equals b, then x minus a plus a equals b plus a. Okay, that's a bunch of gobbledygook. Let's break it down into human language. So, if x minus a equals b, then what we have is an equal sign here, meaning that all of this has to equal all of that. And in order to keep the balances even, to keep the scales balanced, I can do anything to one side of an equation, an equal sign, as long as I do the exact same thing to the other side. So if I have 2 plus, let's say x plus 79 equals 14. That's crazy numbers, but let's say that's what I have. Well, it makes sense that if I subtract 79 from this side of the equation, that it's okay to do that, or I haven't changed the equalness of the equation as long as I subtract 79 from the other side. And that's just logic. If I do something to one side of an equation, of something that's balanced, and I do the same exact thing to the other side, then it would equal the same thing. And the reason I keep saying balance, and you may have seen this in elementary school, some teachers teach it this way, if I have a scale in perfect balance, right? If I put a nickel on this side of the scale, it's obviously going to tilt down on that side. But if I put the same exact mass nickel on the other side of the scale, the same thing is, this whole thing is going to stay in balance. So it doesn't change anything as long as I do the same thing to both sides. And that's all this says, is that the equality holds true as long as I do the same thing to both sides. But I'm more concerned with what I did. Okay, so that's the understanding, the logic behind it. But let's look at what we actually did. I made the a on this side disappear, the minus a, because I added the opposite to this side. So I just made it disappear, and look what I made happen on the other side. I made the opposite of a show up. So I had a negative a, the opposite of a showed up on the other side. That's pretty cool because we're going to use that to solve addition and subtraction problems. So let's do a couple of examples. So example 1, x plus 9 equals 3. Now again, this is sort of like this problem up here, right? What would x have to be in order for x plus 9 to equal 3? Clearly x would have to be a negative 6 because negative 6 plus 9 equals 3. Don't worry that you can do it in your head. What I want to show you is the process that you'll be able to use forever, no matter how complicated problems get. And You should really like me at this stage of the game, because after spending all year so far telling you have to write every single step down, I'm actually going to show you a method that involves less writing. As long as you do it exactly the way I show you, it involves a lot less writing. Okay, let's do it. So let's use this logic here from the property, and notice that what I want to do, so first let's talk for a second about solve. I'm being asked to solve for x. Okay, so solve for x. That means find out what x would have to be. We already know it's -6, but solve for it instead of just use your logic. Well, solve for x really means, in human words, get x alone on one side of the equals sign equals everything else. Okay, so that's what we want to do. So what we want to do is kind of hold this x down, like put your finger on it so it can't go anywhere, and figure out how to get everything over to the other side. So the thing I want to get to the other side is a +9. That's addition. So I can make it disappear if I add the opposite to both sides. And what is the opposite of 9? -9. I know that if I add -9 to this side, it's going to disappear. See, right here. If I add -9 to that side, it's going to disappear, and it's going to appear over here. So I'm going to disappear the 9 that's a problem, and on the other side it's going to become the opposite of 9. And now simplify. X, now it's alone, equals 3 take away 9 is -6, and that's exactly the answer we expected to get. Let's do another one. X minus 2 equals 11. Okay, so same thing. I want to get x alone. -2 is in my way. -2 is connected to x by subtraction, so I'm going to use the opposite by subtraction. The additive inverse is the opposite of the number. -2 on this side becomes a +2 on this side, but on this side it's going to disappear. And now x equals 11 plus 2 is 13. So now I know what x would have to be for that to be a true statement. What if it's written in another order? Let's look at that. Let's do -12 plus x equals 3. Okay, well, I have an x on this side, right here, that I want to keep there, and I have a -12 in the way, so I want to move it over there. So what's the opposite of -12? +12, and it's going to disappear on this side. So now I have x equals 3 plus 12 is 15. Couldn't be any easier than that. So now we need a way to find out if we're right. So we're going to check our solutions. And we check our solutions, right, by putting our answer back into the original equation. So I have x here. I'm going to put that in for the -6. My solution I'm going to put in for my solution I'm going to put in for x. So I get -6 plus 9 equals 3. So that was, remember, we've been checking solutions all along now. So now I'm going to do it. The only difference is I found the solution. Instead of checking to see if this number is a solution to the equation, I have to actually find the number first by myself and then check it. So -6 plus 9 equals 3. So yes, it is totally a solution. Let's do the same thing here. And I like this notation with this little arrow thing and then writing the problem out next to the loop. I think it's very clear and concise note-taking. So I'm going to put in a 13 for my x, -2 equals 11. And I'm not sure if that's true yet. 13 take away 2 is 11 equals 11. So yes, it is a solution. Do it up here too. -12 plus 15 equals 3. Not sure if it's a solution. -12 plus 15, 3 equals 3. It is a solution. So I have solved and checked 3 problems in no time at all. Cool. Okay, so we have the addition property of equality, and based on the work we've been doing, you're probably thinking there must be a multiplication property of equality, and by golly, there is. By the way, before I go on, let's make the point that the addition property of equality includes the subtraction property, because addition and subtraction are the same thing. And it basically says in the opposite, if I had a plus here, then I'd have a minus here and a minus here. It's covered in the multiply by the opposite. So in this case, I actually used the subtraction property because I added a -9 to both sides, and adding a negative is really the same thing as subtraction. So when you have addition and subtraction, this is the process you use. Okay, let's get on to the multiplication. And by the way, multiplication property of equality includes division property of equality. All right. I think it takes longer to write that sentence out than it takes to actually solve 3 problems. Okay, so the multiplication property of equality says that if x over a equals b, then x over a times the reciprocal of a, right, the inverse of a, equals b times the reciprocal of a. And I only put that 1 to show it was a reciprocal. So I've done the same thing I did before with the addition subtraction, only opposite, finger quotes, opposite in multiplication means inverse, right? So let's look at it. Let's look at this one too. Let's break it down. What actually happened when I did this process? I started with a 1 over a on this side, and by multiplying this side by a over 1, I actually made the a's disappear, right? Because x times a over a, you can cancel the a's. And on the other side, I made the reciprocal appear on the other side. Okay, so let's do a couple of examples of those then. What example number are we on? 4. -6x equals 48. Now your book shows you a method that's pretty commonly used now, where you just divide both sides by -6 and then you do that cancel and you do that cancel. But I'm going to ask you not to do that for 2 reasons. One, algebra really is about applying the properties that have been taught already, that you know are true. And you're not actually applying a property when you do that method, you're using a trick. And so you're not really developing the concept, you're just getting to an answer, which to me is not really great algebra. And the second reason is, if you get into the habit of doing that, when your problems get much more complicated later, they get really messy when you do that. And at some point along the way, some teacher is going to ask you to stop doing that, because you certainly don't need to be doing it. You're just doing it because it's a habit that you've developed. So let's let the habit that we develop be the algebra applying a property rather than just a trick that you learned, because that's a better habit. Okay, let's move on. So what's going to happen here? Well, this is okay, so I'm going to solve, which means I need to get x alone. So I ask myself, what's in the way of x being alone? And it's the -6. How is -6 connected to x? Well, it's connected to x by multiplication. If I did that, it would make it more clear. -6 is a multiplication element with the x. So what undoes multiplication, right? And you can multiply by the reciprocal to get that number to equal 1. That's what we're trying to do, is turn this -6 into a 1 by multiplying by the reciprocal. So if I multiply by the reciprocal, and I'm going to write it all out the long way, -6 times 1 over -6 times x equals 48 times, And what do I have to do? I have to multiply it by exactly the same number that I took out, right? Or that I multiplied on the other side, because remember, we're dealing with an equation, so we want the balance to stay true. It doesn't have to have the exact same numbers, but it does have to stay in balance. So if I multiplied by negative 1 over 6 on one side, I have to do the same thing on the other side. Okay, so what happens to negative 6 times 1 over negative 6? Well, that's just the multiplicative inverse, right? So that means it equals 1. So I made it disappear on that side, and what happened? I made it appear on the other side. So I can finish out my problem, and I get x equals 48 divided by 6, which equals, wait a minute, I forgot a minus sign, 48 divided by negative 6, which equals negative 8. If I'm not sure of that division, I can certainly do the reductions, right? 48 divides by 2, leaving 24. 6 divides by 2, leaving a 3. 24 divided by 3 equals 8, and I carry the negative sign over. All right, so let's do a couple that don't have so much explaining, because I think it makes it easier to see. So let's do example 5. Let's take negative 4x equals negative 28. So, doing the math, using the logic in my head, I'm thinking, I want to get this x by itself. Negative 4 is in the way of x being alone. Negative 4 is multiplied to x. So I'm going to use the multiplicative inverse, which is multiply by 1 over negative 4. If I use the multiplicative inverse, negative 4 is going to disappear on this side, and it's going to show up as division on that side. So the multiplicative inverse on both sides means it disappears on this side and shows up on the other side. Now I can just finish up. X equals 2 negatives makes a positive. 28 divided by 4 is 7. Done. 2 more quick examples, and then I'll let you go. X divided by 3 equals 7. Okay, x, I want to keep x alone. 3 is in the way of x being alone. 3 is a division problem on this side, so I want to turn it into the inverse of division, a 3 on this side, meaning it disappears on this side. X equals 21. Last example, it kind of drives the point home for me. 1 negative 3/5 x equals negative 9. All right, so this is a place where now I've got a rational number instead of an integer. I actually never want to do this. Nobody wants to say, oh, well, just divide both sides by negative 3/5. What the what? Why would I do that, right? So this is the thing I'm trying to get away from. As numbers get uglier, we don't want to be doing that. So instead, I'm going to use the same logic I used here, and it turns out multiplying and dividing by a fraction is as easy as multiplying and dividing by an integer. I'm going to say to myself, I want to get x alone. So what's in the way of x? Negative 3/5. How is it connected to x? By multiplication. What undoes multiplication? Multiply by the reciprocal times negative 5/3, and I know because I chose a process that gets rid of it, it disappears on that side. So x equals negative 9 times negative 5 over 3 equals, and at this point I'm going to reduce before I do a multiplication. Why turn this into 45 divided by 3 and then reduce it? Why not just go ahead and reduce it now? 9 divides by 3, leaving a 3. 3 divides by 3, leaving a 1. So now I can take negative 3 times negative 5 over 1 equals 15. Done.